Everyone, I am Dr. Anita Dubey from Government MLB Girls PG College, Bhopal. I am here to deliver lecture on the concept of laws of thermodynamics under the Higher Education Madhya Pradesh session online classes for the students of MSc previous. Myself, Dr. Anita Dubey, professor in chemistry. Currently, I am posted in Government MLB Girls PG Autonomous College, Bhopal. I think that the students should know about the concept and information and the importance of thermodynamics, because the thermodynamics is the science which most influences our daily lives. Thermodynamics is the study of interrelation of the various forms of energy and heat accompanying the physical and chemical processes in a system. It helps us to predict whether the given process is possible or not under given condition of temperature, pressure, and concentration. Therefore, it has been found that the thermodynamics plays an important role in our daily life. After completing this module, students will be able to visualize the application of laws of thermodynamics in daily life, know how efficient things are using energy for useful work, and also the students will be able to know the important terms used in thermodynamics. Now, before we moving on the concepts and the laws of thermodynamics, we should know about the term thermodynamics. We should know about the meaning of thermodynamics and its importance also. The thermodynamics is as old as the universe. It deals with stability of systems and tells what should happen. The term generates from the two Greek words therm and dynamics. The Greek word therm means heat and the dynamic means force or power. Actually, the thermodynamics is the beautiful illustration of natural science, which tells us how can we use energy efficiently and how can we minimize the waste. Therefore, the thermodynamics is very important in our daily life. The subject has therefore proved of immense importance in engineering, physics, and chemistry. Now let us discuss about the various terms which are used in thermodynamics. Any specified portion of the universe which can be real or imaginary and which is selected for thermodynamic study is called a system. The system is defined by a specified boundary which can control the transfer of matter as well as energy and the energy. The value of a property of a system is independent of the process or path followed by the system. The change in the value of property depends only on the initial and the final states. Actually, the system is defined by certain measurable or observable characteristics or properties, which are defined as state variables. Now, the leaving the system, the rest of the universe, which may exchange matter or energy or both with the system, is called surroundings. The system is distinguished from its surrounding by a specified boundary. A real or imaginary envelope enclosing a system is called boundary of a system. Here is the basic diagram showing the fundamental difference between system and surrounding. Now, property of a system. The system is characterized by measurable parameters. These are called properties. The properties of the system are of two types: extensive properties and intensive properties. Extensive properties of a system are the properties which are additive in nature and depend on the quantity or amount of substances present in the system, such as mass, volume, energy, number of moles, entropy, enthalpy, Gibbs free energy, etc. Whereas the intensive property is a bulk property, which is independent of the amount of the substances present in the system. Example of intensive properties include temperature, pressure, density, viscosity, refractive index, specific heat, surface tension, etc. Now, the types of system. A system can be classified as open system, closed system, and isolated system on the basis of the exchange of matter and energy between the system and surrounding. As the figure represents the open, closed, and isolated system, in open system, energy as well as mass both can be exchanged between system and surrounding, whereas in closed system, only energy can be exchanged between system and surrounding. And in isolated system, neither energy nor mass can be transferred between system and surrounding. The example of the open system is the cup of tea, uh, and the human body also is an open system. And the example of closed system is the pressure cooker. And as example of the isolated system is the thermos flask, in which the hot liquid is kept hot for some time. Actually, 100% isolated system cannot be found in nature. But interesting thing is that the universe itself is the isolated system. Now, state of a system. How can we define the state? Actually, the condition of a system is defined by the parameters, by the characteristic parameters, which are the temperature, pressure, volume, density, mass, etc. A thermodynamic state of a system is its condition at a specific time that is fully identified by value of macroscopic properties such as pressure, temperature, volume, density, composition, etc. If the macroscopic properties have fixed values, the system is said to be in definite state. Any change in property changes the system into a different state. The parameters which determine the state, yeah, property of state, is known as thermodynamic variables or state variables. The quantities whose value determine the state of a system are called its thermodynamic variables. The most important state variables are pressure, temperature, volume, mass, and composition. Now, let us discuss about the thermodynamic equilibrium. A system is said to be in thermodynamic equilibrium when its macroscopic property do not undergo any changes with time. The system has three types of equilibrium. Thermal equilibrium, in which the temperature of a system along with temperature of its surrounding do not change with time. In mechanical equilibrium, the system does not perform any mechanical work. This is only possible if the pressure of the system remains same during the whole process. The chemical equilibrium, when the chemical composition of the system does not change with time, the system is said to be in chemical equilibrium. Now let us discuss about the thermodynamic processes and their types. When a thermodynamic system changes from one state to another state, the operation is known as a process. These processes are of different types. The important process is the isothermal process and the adiabatic process. The isothermal process is the process in which temperature of the system remains constant throughout the whole process. The system exchanges heat with its surroundings and the temperature of the system remains constant. For an isothermal process, the change in temperature is equal to 0. If a process is carried out in such a way that no heat is allowed to enter or leave the system during the whole process, it is called an adiabatic process. This condition is attained by thermally insulation the system. For an adiabatic process, the heat amount of heat Q is equal to 0. If the process is carried out in such a way that during the whole process the pressure is kept constant, then the process is said to be isobaric process. For an isobaric process, the change in pressure is 0. In isochoric process, the process is carried out in such a way that the volume remains the same throughout the whole process. For an isochoric process, the change in volume is equal to 0. Yes, here is the another very important process, that is the cyclic process. When a system returns to its original state after completing the process in various stages, then it is said that a cycle is completed, and this process is known as cyclic process. Actually, in cyclic process, the initial stage and the final stage are the same. Therefore, for a cyclic process, the change in internal energy, the change in pressure, the change in volume, and the change in temperature, change in enthalpy is 0, because these are the state variables which depends only on the state of the system. Now we should know about the reversible process. In thermodynamic sense, when a process is carried out infinitesimally slowly, so that at every stage of the process, the system and surrounding remains in equilibrium with each other. This process is called a reversible process. Whereas in irreversible process, the process is carried out in such a way that the system and the surrounding cannot be restored to the initial state from the final state. All natural processes are irreversible. Now, the topic is laws of thermodynamics. The success of thermodynamics in various fields of science is based on the wide application of the well-established laws of thermodynamics, which deal with energy, apply equally to all phenomena in nature. The laws are applicable only to macroscopic system. Yes, this is very important point. The laws are applicable only to macroscopic system. The macroscopic system is one that consists of large number of atoms, particles, molecules, or radicals. The first law is concerned with the equivalence of different form of energy. The second law is concerned with the direction of chemical change. And the third law attempts to evaluate the thermodynamic variables. The first law of thermodynamics. The first law of thermodynamics is a statement of the law of conservation of energy, according to which the energy may change from one form to the another, but neither be created nor destroyed. The first law can also be stated as it is impossible to construct a perpetual machine from which work or energy can be obtained without expenditure of energy. Or in other words, we can say for an isolated system, the energy is constant. Here is the mathematical form or statement of first law of thermodynamics. According to first law, when we subjected Q heat to the system, the sum of the heat given to the system is used to change the internal energy of the system, while the remaining part of the heat energy is used in doing work by the system. So mathematically, we have the equation Q is equal to del E plus W. Here, Q is the heat energy subjected to the system. W is the energy given by the system in the form of work. And del E is the change in internal energy. If the work is done by the system on the surrounding, the change in internal energy can be given by the equation del E is equal to Q minus W. Now, we calculate the heat changes at constant volume and at constant pressure. At constant volume, since uh, there is no mechanical work done by the system when the process is carried out at constant volume. Thus, the equation first becomes del E is equal to Q. And here the process is carried out at constant volume. Therefore, the subscript V is put on the heat energy Q. Therefore, the equation becomes QV is equal to del E. This is the equation second. Okay, starting with. Okay. The first law of the mathematical form of first law of thermodynamics, when Q heat is subjected to the system, some part of the heat is used to increase the internal energy of the system, and the remaining part of the system is used to perform work by the system. Uh, Previously, we discussed about the heat at constant volume, which has been found to be QV is equal to del E. Now, let us uh, calculate the heat energy at constant pressure. Suppose a change of state of a system brought from initial state to the final state, and the initial and final states are represented by the subscript 1 and 2 respectively. Then when a process is carried out at constant pressure, the volume is allowed to change from V1 to V2. Then the work done by the system can be given by W is equal to P V2 minus V1, and the change in volume is denoted by del V. Therefore, the equation can be represented as W is equal to P del V. The equation, we know about the equation first, that is the del E is equal to Q minus W. From equation first, del E is equal to Q minus P V2 minus V1. In place of W, W is the work performed by the system. In place of W, we put here P into V2 minus V1. Therefore, the equation becomes del E is equal to QV minus P del V. Now, where del V is the change in volume at constant pressure. Since from equation second, we know that at constant volume, the heat energy QV is equal to the del E. Therefore, in place of del E, in the equation 3, we can put the QV. And we know that P del V can be replaced by del N RT. Therefore, the equation 3 becomes QP is equal to QV plus del N RT. Now, Let us discuss about the heat content or enthalpy. As we already deduced the equation that at constant pressure, the heat energy Qp is equal to del E plus P del V. Here, Qv is the heat is subjected to the system at constant pressure. Del E is the change in internal energy of the system. P is the pressure and del V is the change in volume. If the initial state is represented by the subscript 1 and the final state is represented by the subscript 2, then in place of del E, we can put E2 minus E1, the internal energy of the final state minus in internal energy of the initial state, the difference in energy, internal energy. And in place of del V, we can put the equation V2 minus V1. Thus the equation becomes QP is equal to E2 minus E1 plus P into V2 minus V1. Or QP is equal to, by rearranging the equation, we find that QP is equal to E2 plus PV2 minus E1 plus PV1. As we know that the internal energy and the volume, these are the state properties. Therefore, the quantity E2 plus PV2 and E1 plus PV1 must be dependent only on the state of the system. Hence, a new quantity is defined by the equation H is equal to E plus PV, where H is known as heat content or enthalpy. This new thermodynamic property, that is the heat content or enthalpy, is also a state variable. Therefore, H1 is equal to E1 plus PV1 and H2 is equal to E2 plus PV2. Hence, from previous equation, the heat energy at constant pressure is equal to H2 minus H1. Change in enthalpy. So Qp is equal to del H. And if we combine the equation 3, 4 and 6, we get the final equation del H is equal to del E plus del N RT, where del H is the change in enthalpy, del E is the change in internal energy, change in number of moles, R is the gas constant and T is the absolute temperature. Now let us discuss about heat capacity. Heat capacity of a system between any two temperatures is defined as the quantity of heat required to raise the temperature of the system from lower to the higher temperature divided by the temperature difference. It is usually denoted by C and has two values. One value is the heat capacity at constant volume, which is denoted by Cv, and another value is heat capacity at constant pressure, denoted as Cep. The heat capacity is defined by the differential equation C is equal to del Q upon del T, where del Q is the change in heat energy and del T is the change in temperature or temperature difference. The heat capacity of a system at constant volume is defined as the increase in internal energy of the system per degree rise in temperature, and it is given by the equation Cv is equal to del E upon del T at constant V. Similarly, the heat capacity of a system at constant pressure is defined as the increase in enthalpy of the system per degree rise of temperature. Thus, the equation is Cp is equal to del H upon del T at constant V. Since the first law of thermodynamics does not say anything about the direction of the flow of heat and it does not say anything whether the process is a spontaneous process or not. Therefore, it is required to present the second law of thermodynamics. Cauchy's statement of the second law is like this: it is impossible to construct a heat engine which will continuously transfer heat from a single body and convert the whole of it to work without leaving changes in the working system. In terms of possible processes, Clausius stated that heat cannot pass spontaneously from a colder body to a warmer body. Spontaneous processes are those which occur of their own accord and can be made to do work under proper conditions. But in the natural irreversible ways, the maximum work cannot be obtained. Second law of thermodynamics can be explained on the term of entropy. In terms of entropy, in all actual processes, physical or chemical, occur in nature, take place in such a way that the sum of entropies of interacting thermodynamic system increases. Change in entropy for reversible processes given by the equation del S is equal to del Q reversible upon T. In all actual processes, the entropy always increases. The actual processes are irreversible processes. The entropy of the nature is increasing, or the entropy of the nature is always more than zero. The third law of thermodynamics. From quantum theory, the heat capacity of solid should tend to zero at 0 degree Kelvin. Hence, Nernst heat theorem can be extended to limit when the absolute temperature tends to zero, Cp is equal to zero. Heat capacity at constant pressure becomes zero. Similarly, when the temperature tends to zero, absolute temperature tends to zero, at temperature zero, the motion is stopped. Therefore, for a pure crystalline solid, the change in entropy is zero. In other words, we can say that the entropy of a system approaches a constant value as the temperature approaches absolute zero. In other words, the absolute entropies of product and reactants in solid state are same at 0 degree Kelvin. Hence, we can conclude that at absolute zero, all solid substances have the same entropy. Planck, on the basis of quantum theory, stated that the entropies of pure solid approaches zero at 0 degree Kelvin. Now, zeroth law of thermodynamics. The zeroth law of thermodynamics concerned with the thermal equilibrium and forms a basis for the definition of temperature. It states that if two systems A and B are in thermal equilibrium with a third system, C, then A and B will also be in thermal equilibrium with each other when placed together. If the systems are in thermal equilibrium, no heat will be flowed. This is the diagram showing the zeroth law. The zeroth law of thermodynamics states that if two thermodynamic systems are each in thermal equilibrium with the third system, then they are in thermal equilibrium with each other when placed together. Now, let us revise the laws of the thermodynamics. We discuss about the application of first law of thermodynamics in daily life. The transformation of electrical energy into radiant energy in light bulb is the example of first law of thermodynamics. Similarly, plants convert solar energy into chemical energy by photosynthesis. The human body also obeys the laws of thermodynamics. Here the picture is the basic diagram to show the first law of thermodynamics, which states as the energy can be transformed from one form to the another, but energy can neither be created nor destroyed. As we know that thermodynamics is the science that most influences our daily life because so many of devices which we use, for example, heating and cooling systems in our house, all types of engines, design of buildings and vehicles, all types of vehicles that we use, such as cars, motorcycles, truck, tractor, ships, aeroplanes, work on the basis of second law of thermodynamics and Carnot cycle. And the heating and cooling systems and the design of building and vehicles all are incorporated with the concepts and information of thermodynamics to make them perform well. Here are some example of the second law of thermodynamics in daily life. Steam power plants, spark, ignition engine, jet engine, refrigerator, air conditioner system, and heat pumps. And the diagram shows the simple illustration of the second law of thermodynamics, which shows that in spontaneous process, the heat can be flowed from hot reservoir to the cold reservoir, but it is impossible to flow the heat from cold reservoir to hot reservoir spontaneously. The third law of thermodynamics, which states that at absolute zero, the entropy for a pure crystalline substance becomes zero. Entropy change becomes zero. The entropy is constant at absolute zero. Since at absolute zero, theoretically all modes of motion stops, no vibration, no rotation, no translation. Thus, the third law of thermodynamics states that the entropy of a pure crystalline substance at absolute zero is zero. Application of third law of thermodynamics is the third law of the thermodynamics is used to predict the change in different materials with changing temperature, and it is used to determine absolute entropy of the solid. Now for further reading, please refer Advanced Physical Chemistry by Gurdeep Raj, Advanced Physical Chemistry by J. N. Gurdu and A. Gurdu, and Introduction to Chemical Thermodynamics by R. P. Rastogi and R. R. Mishra. And this is the site Wikipedia. Now the time, assess yourself. Here the question first. It is very simple question. The value of del Q in an adiabatic process is, as we already stated that in adiabatic process there is no heat is allowed to enter or leave the system. Therefore, the answer is the solution is the 0, C. The second question is if the pressure of the system remains constant throughout the process, the change is called. We already studied or discussed that the process which is carried out at constant temperature is called isothermal, and the process which is carried out at constant volume is called isochoric process, and the process which is carried out at constant pressure is known as isobaric process. Therefore, the answer is isobaric. Now, I hope the lecture will help you to increase your learning potential. Thank you.